Next, I want to look at a problem also in axiosymmetry where we expect a pipe This is also AC magnetics, also axial symmetry. I'll zoom into the model here. That's a little farther than I wanted. It's the air region. The left coil, this is the right coil. And this is the pipe, which you can see that has a notched defect here, since this is part of the air region. Also, I've included a single node to use as a test point. Now, since these coils are counterwound, from symmetry, we expect that there's no X-component magnetic field at the test point. So we can monitor the X-component magnetic field as we translate the pair of coils along the pipe. First, let's look at the solution. This is essentially 100 hertz, which wouldn't be in the operating range of a pickup coil. However, a Hall effect sensor, flux gate, or a SQUID would be more suited for the ultra-low frequency range. Okay. So as you can see, the counterwound coil is producing a magnetic field here that won't have an X component. The magnetic field has the Z component here, but it doesn't have an X component. And with a defect-free pipe, there won't be any X component either. Now, the presence of the defect will contribute to an X component in this region. So let's go ahead on and scan it. Okay, once again, I'm in label mover serial analysis. I want to add values. I'm interested in the X component magnetic field at the test point. Okay, so I've selected the test point. I'll go to the flux density, and I want the X component. Let's add that. Okay. Now let's record steps. Okay. I can change the properties. I'm not sweeping the frequency now. I'm going to be translating this pipe. Okay. I'm going to move it. Actually, we realistically want to translate the sensor, but I'll be translating the pipe, which has the same effect. And let's give it 1 centimeter displacement in the interest of time. Oops. I want to translate the pipe, so we have to select the pipe, and this is the displacement. We'll add a step. Okay, I've translated the pipe to the right 1 centimeter, and I'm going to repeat that step. Okay. I've repeated it 4 times, so we've translated the pipe 4 times. The test point has passed over the defect at this point. Now the right-hand coil is above the defect, as you can see here, just underneath the record steps. I'll repeat it 1 more time. Okay. Now let's close this, and we get results. As you can see that the X component field is quite small. Initially it would be 0. It would be 0 if there were perfect symmetry in the problem, which is broken by the defect. And if you want to speed up the simulation, you could bring in the edges of the solution region and so forth and reduce the number of nodes in regions where you're not interested in the field distribution. There will be some edge effect as our coil approaches the edge of the pipe as well. Okay, we've finished our scan, and now we can look at the plot of the result here. And now this is the defect signal as we pass over the notch in the pipe. If you increase the number of steps, say 0.1 centimeter, of course it'll take 10 times longer, but you'll have a much nicer profile of the defect signal here. Next, I want to look at a pulsed eddy current simulation. And I will close everything so don't get confused. Okay, this is pulsed eddy current. Now this is different. We're using an XY symmetry here. As I mentioned, we would look at, and this tool fits it in the window. If we look at the geometry file, this is the air region. It's aluminum. This is our flaw. And I've given the flaw a permeability of 1. I could have assigned it air region as well. Once again, the aluminum has a conductivity of 2.7. 10 to the 7. I've assigned 0 vector potential to the edge of the solution region. Now the inducer has a time-dependent current flowing through it. So this is I've assigned a boundary condition on the tangential field, which is equal to the surface current density. And this is going to be 1 times the sine of the sine, which gives a square wave. And the period is 0.2 hertz. And later we can look at the profile that, so you can see what exactly that square wave looks like. Let's go ahead and solve. It's already been solved. However, want to show that solutions of time-dependent problems take a little bit more time than the AC magnetics problem. And my computer is not the fastest computer here. 1995 Toshiba. (2005) actually. So we're looking at an animation of the flux lines. Of course, the magnetic field lines are going to be tangential to the flux lines here. We want to look at the eddy current density. Okay, and as well I can disable the magnetic field lines if I just want to look at the eddy current density as a function of time here. So you can see that there's no eddy current that's flowing in this simulated flaw here, which is actually a sort of a groove in the conducting plane. The current in the sheet inducer is flowing out of the page. In the absence of the defect, there will be no Y component field at the very central region above the sheet inducer. So a magnetic sensor, such as a Hall probe, SQUID, or a fluxgate, oriented sideways here, would have a null response in the absence of defects. So what we'd like to do is investigate the field distribution here, especially the X component or the Y component. We can look at a time plot of the magnetic field. And I want to look at the point directly above, which is located at 2527. I want to look at the flux density. Okay. So you can see that there's three curves of the flux density. We're looking at the magnetic field and its X and Y components. You can see that one of the components is very small. That would be the Y component. That is due only to the defect. So let's go ahead and switch off these two components, and so now we can see the defect signal, which is roughly an order of magnitude smaller than the B and the BX components. One thing I want to do is just look at the signal of the sheet inducer itself. If I go back to my model, my aluminum region, I'm just going to switch it to air. The flaw has permeability of air. Now I'm going to solve this. Okay, so this is just the flux density due to the sheet inducer. Of course, the edge of the solution region will always influence it, and you want to have those pushed out as much as so it doesn't affect the region of interest here. And I can look at a particular instant. I can look at the time curve. Okay, I'll pick this point, make a time plot. And this is actually a time plot of the vector potential, which you can see is a square wave here. The SIGN of the SIN essentially gives us a square wave.